approximations that we have done now to get the fluxes. And we use also the approximation that we have been using for the source term. So inserting these approximations, that is of gamma of the derivatives, and the approximation that we have been using for the source term, that was the average of the source times the volume of the control volume is approximated by the uniform part of the source term plus the part that is dependent on the node P times the unknown in there. So that is the same approximation as we used in 1D. And we insert that into the equation that we have been discussing, and I think that was 33, was the integral equation. We obtain then the following. On the left-hand side we have 0. Of course, again, we have no time derivatives, and we have no convection, velocity is 0. So we start with the diffusive flux at the eastern phase. That is the diffusion coefficient there, then approximated either by arithmetic or harmonic mean, or if it's constant, then we don't have to do any approximation, times the area there, that we can also get exact, and then we do the approximation of the first derivative, as we discussed in 1D, by taking the difference between the values at E and P and divide by the distance between these nodes, P and E. Then we have the minus, because that was coming because the normal is in the negative x direction at the western phase, and it is just the same. It is the diffusion coefficient at the western phase times the area at the western phase, and now the derivative there is approximated by the value at P minus the value that is capital W divided by the distance between capital W and P. So now we have taken into account the eastern and western diffusive fluxes. Now we get the northern one. The northern one is then the gamma n, little n, times the area at the northern phase, times the derivative, which is phi n minus phi p, divided by the distance, now in the y direction, between P, node P, and the northern neighbor N. From the southern, we get a minus, because the normal is negative y direction. We have the gamma S, area S, times derivative is approximated then by phi P minus phi S, divided by the distance between S and P. And then we have the source term, and that is the term that we have here. That is then the uniform part of the source plus the node-dependent coefficient P times the unknown there. So then we get this expression here. And now we do the same thing as we did in 1D. We write everything that is dependent on P on the left-hand side and the rest on the right-hand side. So, and that gives us then, so reordering yields then the following, that is then 36. Well, we start by this one here, phi p, that gets with a plus on the right, on the left-hand side. So, and then we get the gamma W, area W, divided by the distance between capital W and capital P. The same now for the eastern. This one here goes over, and it also gets a plus sign. Gamma E, AE, diffusion coefficient times area at the eastern phase divided by the distance between node P and E. for the northern phase, we get this contribution here, depending on phi p on the left-hand side with a plus, fusion coefficient at the north, area at the north divided by the distance in y between, well, here I made a little, let me correct that, because I took here west first, then I should also take the south here first. And that is this one here, and that gets anyway also with a plus on the left-hand side. And then we have here the S, capital S, capital T, distance between them. And now we take the northern one, gamma n, an divided by the distance between P and N. And that is then multiplying our unknown at the node P. On the right-hand side, we have now the rest. And if we start with the western contribution, we'll see we get here a minus minus. That gives us a plus. So that gives us then the gamma little w, the area at this phase little w divided by the distance between w and p. And that is multiplied by phi w. Then we have the contribution from the east, that is at the very beginning here, so this contribution here. And that is the gamma E, area E divided by the distance between P and E, multiplying our unknown at the eastern node. And then we have a contribution, let's see that little space here for giving names to these. We have the gamma now at the southern face, that is minus minus, that gives plus, so that is AS, gamma S times AS divided by the distance between S and P times the unknown at the southern node, plus the contribution from the north, that is this one here, gamma north, A north divided by the distance between P and N. And that is multiplied by phi unknown at the northern node. And let's see, now we have to take the source term into account. That is easy here, but here I need to change a little bit, because the SP, that will also go on the left-hand side. So here we have to correct a little bit to get the minus SP here. That is coming from this coefficient of the source term. So that is now entering here. The uniform part is here. So then we have it. So we need a little space here, because as in 1D we shall give now these coefficients, they will get names. And we do the same, we use the same names as in 1D. For the coefficient multiplying AP, that is this one here, that is containing then all these contributions, and that is then the coefficient AP. So that is the coefficient AP. And here we have then the AW, and that is then capital, and this is here the A capital E, this is the A capital S, this is the A capital N. So then we have our contributions here, and then we can write this equation that we get from the discretization using the finite volume method in the following way. So equation 36 can be expressed as that is now the following. That is 37. That we have AP times phi p is equal to A capital W phi capital W plus A E phi E plus A south phi south and then we have here the plus A north phi north plus the SU. So that is then the equation that we get. And the coefficients we have identified here. Very important again here is the fact that we can see by looking closely at the coefficient AP. The coefficient AP consists of the sum of all neighbors. AW, AE, A south, and A north, minus the coefficient from the source term. So that means we have here again, as we had in 1D, the situation that AP consists of the coefficients of the neighboring nodes minus the coefficient coming from the source term. So that we can write also a little bit shorter as the sum over the neighbors, where we have the A and B. So that is this minus the SP. So the NB that we are using here, that is then the neighbor. The neighbor coefficients. And they are, as you see, W, E, S, and N. Now, to express this as a system, we shall use a little different way, because here we have still unknowns. And when we write it as a system, we have to bring that to the left-hand side, so that we can collect all the unknowns on the left-hand side to give us then the matrix that is described by this. So that means the equation 37 can also be written as the AP times the phi p. Now we can use this short notation with the neighbors, minus the neighbors coefficients, and that is then the A NB, the phi NB. You see, now the meaning is the AP, phi p, that is untouched. And then we bring these coefficients on the left-hand side. So this means A capital W, phi capital W, and so on. These four summands are then written here on the left-hand side. And that is then equal to the uniform part of the source term. So that is then what we get. And we can also write this now in a little different form. Let's see. And the form that I'm using is now the following. Let's see. So I'm using now, this is equivalent to saying, if we introduce the index notation, that we say this is I, A, I, J, the unknown phi ij. So what I'm doing now is I go from the letter notation with P, E, north, south, west, so on. I go to the index notation. So the E is the I plus 1j, The W is the I minus 1j. The north is the ij plus 1, and the south is the ij minus 1. It's just by our index notation we get this naturally. So then I introduce some new names here. For the minus AW, I'll introduce the name Bij. And the unknown there is then the phi I minus 1j. And for the minus AE, that is in here, I introduce the notation Cij. Remember, that is very similar to what we did in 1D. We called that B and C also. So that is then the phi I plus 1j. Now we have to introduce also names for the minus AS. I give you the correspondence in a minute, and there I introduce the name Fij. So that is relating to the minus AS, and that is then going to ij minus 1. And then we have the minus AN. There I introduce the Gij, phi ij plus 1. And all that is equal to SU. And that is called now, in this notation, as we did in 1D, Dij. So now the correspondence here is then the following. Let's see. The correspondence is, so that is, let me see. So we have the 37, that is that one. So in 37, and the new notation, let's see if I give that the name 38 here, this one. 38. Then we can make here a little list and identify the coefficients with the letter notation and with the index notation. So that is Aij, and the minus A capital W is then the Bij, the minus AE is the Cij, and the minus A south is the Fij, and the minus A north, these are capital letters all, that is Gij, and the SU, uniform source term, is then called Dij. So then we have this correspondence. Okay, now we want to use derivative boundary conditions. That means we give values everywhere at all boundaries for phi. So we prescribe the values of phi at all boundaries. And then we can include these nodes. For example, this was the node 1, 0. This is the node 0, 1. And we can include them all as unknowns. But they are determined by the boundary conditions. So then we use these boundary conditions, and we use for the interior nodes, we use this connection here. That gives us then the connection to the neighbors. And all that will lead to a linear system, provided that gamma is not dependent on the solution. Otherwise, we would have to do iterations, but in each iterate, it would be a linear system. So now we want to see what system do we get. So let us try to rewrite that. So, let's see. So then I need space, and you need also some space. So we shall use this form with the indices. So that is also in the program that you have the skeleton as in 1D. First the coefficients are determined, the AP, AW, AE, and now also AS and AN. And now we look what system do we get from that. So again, we assume then that we have directly boundary conditions. So, let's see. So we get them using, I want to save a little space. So using this relation 38 coming from the finite volume discretization and using directly boundary conditions, let's see, for example here this one, that would be the phi, let's see, that would be the phi I0 that I'll call the phi IC. Let's see if I'm doing it right. So that is then at YC. And the boundary condition at this, so that was the one that we have here. So this is then the phi I, that is then the phi IC. And the index it gets is phi I0. At this boundary condition here is then the phi I, and that is then at nj plus 1. That will be then the phi ID. So this will be the phi ID. So that is given. In the same way we can do it at the left boundary. For example, in here, that would be the phi, it would be the index, first index would be 0, second index j, and that we call then the phi, it is at xa, so aj. So this boundary condition is given here. At this boundary here, we have the phi, the index here is ni plus 1. Ni plus 1j. And that will be given the value phi, will be given the value phi ni plus 1b. It will be at the b boundary. So there, everywhere we have boundary conditions. Now, the boundary conditions for simplicity will be included in our system. And we start then with this, we can order it as we want. But if we order it as we have also done in the exercise 7, we order this, that we order the I going first. So we take then the vector phi, and we take it here, that would be 0, 0. That is, would be the point here. That is, we can give that. That's no problem. And then we have these unknowns here. But they are given by the boundary conditions. So what does that mean? So then, so doing the directly boundary conditions and using 38. So 38 and directly boundary conditions, we get equation what we call now 40. Let's see. This, no, 38. This is 39. 39. So now we need a lot of space here. And we shall first implement the boundary conditions at the boundary y equal yc. So we start here. So then we'll have a 1 here. We will have many 1s here. 1, 1. And the unknowns, that they are then getting, let's see, somewhere further to the right. So here we have our matrix. Problem is the blackboard is too small, so I tried just to pick the part of the matrix that is in the upper left corner. So the unknowns here will be the phi, that will be the phi A0, will be the one here, or it will be the phi C0. Let's see. We have that is the phi, where do we have that? The phi 0c. But the index for the phi is 0, 0. The next one is the phi 1, 0. And then we continue here, and we have the next will be the phi ni 0, and the next will be the phi ni plus 1, 0. So these are our unknowns, including the point at the boundary, up to here, including the point at the right boundary. So this is equal to, now you can see, we will have here everywhere 0. So all what we have here is 0, and the rest is also 0. We'll have 1 times phi I0, that will be the value that we have down here. And that will be, let's see, if we start with the phi IC, it will be the phi 0c. And that will be the same as the boundary condition here. That will be the same as the phi A0. That is because the corner points must be the same. So the next is easier. That is this one. That's the phi 1, 0. That is equal to the phi 1c. And so on. And the last one that is corresponding to this one, that is the ni0. And that is getting the boundary condition. Let's see, that gets the boundary condition. No, we are still here, not yet here. So that gets the NIC, and the last one gets the NI plus 1 C, and that is because of the boundary condition here, the same as the B one. So this one here. And that is the same as the phi, that is 0b. So that is what we get from this part here. So now I try to adjust that they are roughly at the same row. So we get then this one. Rest is 0. So this is just saying that we are implementing the boundary conditions at the boundary YC, including the points at the corners. Now we start with these points here. So we get now, and we include also the boundary condition here. That is the phi 0, 1. So that is the first part here. That is, now we get the phi 0, 1, the phi 1, 1, and so on and we get the phi ni1 and the phi ni plus 1, 1. So then we include all the unknowns, we include the boundary points and the unknowns in all cells in the first row. So they have the second index 1. And we include also the boundary here. So, and then we ask, what will we get for that? So the first thing that we will get is that we will get the boundary conditions. They will enter from the south. Because when we are here, well, first let's see we will get, this will be the first one. So it will be the 1, 0 will be involved, and we will have no contribution from here. That means we will have a 0 here, and we will have the F. The first F will we get here. It will be the F11. The F11, and then we will continue that to the F. Well, the problem is I need more space here. Fni1. And the last one we will have a 0. So then we will have this block here, and they will then multiply these values here. So we'll have 0 times this, then we have no contribution from this point, but we will have a contribution from the southern boundary. F11 times phi10, that is this one here, that will correspond to this one here, F11 phi10. So that will be there. So then we have taken the southern contribution into account. Now we'll take into account the western and first the western, the center point, and the eastern. So then we will get a contribution here, and that will be the boundary condition. Let's see. I have a 1 here, and that is then getting to the phi 0, 1. Here we have to implement the boundary condition. That is the phi A1. Let's see if I'm doing right. Yes, this is the phi A1. That is the boundary condition that we are implementing here. And for the rest, we will have then F11. So this is just the boundary condition. The rest is 0. Here it gets now interesting for the second row. There we'll have the western phase getting into play. The B11, the phi 0, 1. So here we are then taken into account the boundary condition that we have here. Let's see, am I right here? Let's see, phi, no, here we are taken into account now actually the one that we have just discussed. So this one is then taken into account. Phi 0, 1, yes, because that is the western boundary. That is taken into account by this. Then we have the center coefficient that will get a 1, 1, 1. That times the unknown. That is corresponding to this one here. And then we will have the C11, and that is taken into account the phi 2, 1, which is the next neighbor here. So, and this will continue all the way down until we get to B, that will be Ni1, A, Ni1, and C, Ni1. And in the end, we will take the boundary condition at this point into account, that gives us the 1. So then we get a block here, and the rest here is just 0. Also what we had here is just 0. So then we have taken that into account, and now we have to write these guys here. They are getting then the boundary, the right-hand side. So the D1, 1, and so on, and the DNI1. And here we will have again the boundary condition from the right, phi B1. Phi B1. So then we have that taken this boundary condition into account. And then we have now taken into account everything except for the northern contribution. So the northern contribution will get in, and they will follow now below here. So that is, so I need some space now, because now so this is, as I write it again, j plus 1. So now we have here then again a part, and the part that we have here is then taken the phi, let's see, that would be the 0, 2. And we would have here the phi 1, 2, and so on, and the phi ni2, and the phi ni plus 1, 2. So that would be the next bunch of unknowns, and they will then take into account the northern neighbors. So we get here again a block that is then working on these. We will nothing have for the first, because there we have just the boundary condition. And the northern contributions here, they will get into play by the G11, and we will continue all the way down to the GNI1, and we will have a 1 in the corner, 0 here. So they will take into account then the northern neighbors. And this pattern will continue all the way down to the, so we go, then we take them this, this, and this, so we will continue in this way until we come to the upper boundary. And that we will take into account in a similar way as we took into account the boundary at the lower boundary. So what you see is, what we get in the end is a block tridiagonal linear system. So this here will continue, and I can take that away now, finally. So this will continue all the way down, and also this, and also the right-hand side, in a similar pattern as we had here. Let's see the phi. Well, I think you can see now the pattern. That would be the phi A2, the phi 1, 2, and so on, the phi Ni2, and the phi B2, the phi B2, and so on. So these are the right-hand side. This is the right-hand side vector. And all what is here, what has nothing, just has a 0. So we will have, in the end, get this structure, and that corresponds to a block tridiagonal linear system. Just let me show it to you in the lecture notes. So here we are. So that's the system what we will get in the end. You see the I is the identity matrix. This is then called the capital B1, capital A1, and the capital C1. this bunch is called the phi 0, all this vector, the phi 1, the phi 2. The dc from the boundary condition at yc, the phi 1, the phi 2. Sorry, the d1 and the d2. So in this way, you see we get in the end a block tridiagonal linear system. But if you look at this matrix structure, it shows you that we get something in the diagonal. Ones will be a's all the way down. In the end, it will be again ones. And then we will have a neighboring diagonal that is the c above and the b below. But we have a further diagonal here with the g's and here with the f's. So altogether we'll have 5 diagonals. So this corresponds at the same time to a matrix with 5 diagonals, which is called a pentadiagonal matrix. So, and then we need to solve that. So tomorrow we'll look at that again, so that we know this structure, and then we'll think about how to solve that.